Hello Mindsetters, welcome to today's Grade 12 Physical Sciences show, proudly brought to you by Macmillan. I'm Katleho. Today we have a special revision lesson on motion and work. We have selected highlights from lessons shown earlier on in the term just to help you guys revise all the work we've done together in the first term. You can download the notes for today's show as well as other shows on learnextra.co.za/live. And also guys, please post all your questions and comments on our Facebook page, which is facebook.com/learnextra, as well as on Twitter @learnextra. Guys, please, let's get on with today's lesson.
Let's start taking a look at a very simple situation. There's two trolleys, they're headed for each other. I just want to draw your attention to the diagram. So what I'm going to do now is I'm going to highlight the various motion of these objects. Okay, so I've got object M1 on the left. The reason that I use M1 is because that's my first mass. It has a mass in kilograms. It is heading with VI1, which means the initial velocity of that first object. The other object, M2, is headed towards it with its own velocity, so VI2. Now they both have their own momentum. Now, something you'll get quite used to in conserving all of these is that I'm going to have two diagrams. I'm going to have what happened before the collision, and I'm going to have what happened after the collision. Those two must be very clear pictures. So I've shown you what was happening before. And when I push two trolleys closer together, you know exactly what's going to happen. These two trolleys are going to collide. The minute I see a collision, I know, this must be to do with momentum or impulse. But when I take a look at them as a collection, now a lot of grade 12s are saying, well, should I use impulse calculations? Should I use conservation calculations? Guys, you can use both. It depends on the question. If I'm asked to conserve momentum, I look at the whole system. The system is M1 and M2 all together. M1 and M2 together make a system. So there we go. So M1 and M2, that is my system. These two objects make up my system. The reason that I put them on these nice blue wheels is because that allows them a frictionless environment. They're going to slide right along until they strike each other. Let's see what happened after the collision. Now, if they're exactly the same size and they just bounce off each other and they separate, let's take a look at what happens over here. I still have M1, I still have M2, but look at what they're doing. The final velocity of the first object is now away. It's changed its velocity. What about the other one, VF2? It's also changed its velocity. So they came in, before they were headed towards each other, then afterwards they were headed away from each other. Most of you have done this before with a toy car. So two cars headed towards each other, you push them and they strike each other and bounce off again. Now this is quite hard to visualize without starting to take a look at one of those animations, and that's exactly what we're going to do in a moment. But before we do, I want to show you how to apply the principle. Let's see what it actually means in an equation. Then we're going to start playing around with the fun stuff. So if I've been given a situation of before and after, here's the trick, grade 11s. Sorry, I say grade 11s because this is grade 11 work. Grade 12s, this is for you. Now, when I try to conserve the momentum, I need to have a momentum term for each individual object. M times V is momentum. So what I'm going to do is when I start to conserve this, my first step is always to state the conservation of linear momentum. The P initially is equal to the P final. That means that the momentum initial equals momentum final. I didn't lose any. The total amounts are going to remain the same. Now, lots of you at home are going, I don't really believe you because the velocity's changed and velocity makes momentum. And how is it possible that if the velocity's changed, the momentum doesn't change? Guys, have faith. We're going to take a look at it in a moment. Now, how do I apply this? I want you to see that when I write out this full equation, this one is not given to you, but it's a lot easier than you think. what I'm going to do is I'm going to run through and highlight the important pieces of information. Okay, so follow the yellow pen. What we're going to be doing now is we're going to be taking a look at the first object's mass and its velocity. If I multiply those two together, I get the first momentum. So that is the initial momentum of that m1. So m1 times its initial velocity will get me a momentum. Each separate object needs to be treated separately. So again, m2 is currently separate. That means that it's away from the other object. So m2 over there, with its initial velocity, will go and get me the other initial momentum. So I had two objects, I had two momenta. Guys, this is how you figure out this equation. M times v gives me momentum. So for every object I see, I need to say m times v for every object. So here we go, m times v, m times v. We did it twice because there's two objects. What about afterwards? What we're going to find is exactly the same thing. So for final, let's follow the yellow pen. There we go. I've got m1, I've got vf1, the final velocity 1. There is the momentum, guys. It's right in front of you. So m times v again. What about the last one? m2, vf2. There's my last momentum. Okay, well, this is starting to get a little bit mathsy, and I'm starting to itch to play with some experiments. So what I'm going to do is I'm going to ask you to go through to that PhET simulation. Now, that PhET simulation I've already got loaded up. It's called Collision Lab. I'm going to show you a little bit about Collision Lab, and we're going to try and see what's going on inside here. Now, I've already set up the program. I just want to show you some of the shortcuts inside the program, which might make your life a little bit easier. So what I've decided to do is I've decided to show the velocity vectors. So what I'm showing you over here with the cursor is that I can show the velocity or not. So you can actually change this. So back onto here, I've told my particular experiment that I would like to have the kinetic energy of the system. Now, before we get too confused about that, we're going to take it away for now because I want to show you some other cool stuff on here. Now, the really nice thing about this is you can use your mouse to actually drag these objects around. You can change their mass, you can change their velocity. And then what you can do is you can let the system happen, or you can let the system work. Now, before we do that, I want to draw your attention to this little slider bar on the right here. I see some words over here. It goes elastic to inelastic, and I can change this value quite a bit. I can go from a maximum of 100% down to a minimum of 0%. We'll explain the meaning of that in a moment. But for the moment, I just want you to set that at around about 50%. So there we go, 50%. We're going to leave it right there. Now what we're going to do is we're going to do a collision. We're going to collide two objects. Now the really cool thing about this is you can tell exactly how much of the velocity and the mass and everything you've got. You can see all the numbers in front of you. So I've got object 1, which is a red snooker ball over here. Then it approaches a larger green snooker ball. Now, what I can do is I can start to drag and change the velocity. What I want you to notice, and this is something that we haven't talked about a lot, is I haven't talked about this number at the bottom here, this momentum, having a sign. Guys, this tells me direction. What I want to emphasize and what I want to just drive home is that I'm going to give this object some momentum in the one direction, and I'm going to give this object some momentum in the opposite direction. Guys, direction is everything. So what I've done is I've given object 1 a momentum of a half a kilogram meter per second. So I'm actually going to draw on here. What I'm going to do is I'm going to make some notes on here, and we are going to attempt to follow each other. Okay, so there we go. I'm going to be dealing with momentum on the left-hand side. Let me actually try to see if I can change that color slightly over there. All right, so I'm going to be dealing with a momentum over there, and I'm going to be dealing with this momentum over there. I want you to notice that those two are the momenta before I've let the system work. The red object had a momentum of 0.5, but it's positive. The green object has got a momentum of -1. Now, I want you to note that the green object is much, much heavier. It's got a bigger mass. It has a mass of 1.5. The smaller object has got a mass of a half. Now let's see if momentum is conserved. I'm going to let these balls smash into each other and collide. I want you to follow these numbers. So at the moment, I know that momentum of object 1 over here, let's write it out. Momentum 1 of my object here is a half. Momentum 2 at the moment is -1. So I want you to get out your calculator and find me the total. Actually, you should be able to do this inside your brain. So what is the total of positive a half and -1? I know that the momentum before the collision at the moment is -1/2. So let's allow the collision to happen and see if the total is exactly the same. So just a reminder that at the moment, initially, I've got -1/2 kilogram meter per second. Let's see what my momentum will be once I've allowed these two objects to collide with each other. So let's take this away. Right? Let's take all the ink away. Let's let the magic happen. You know what's going to happen. These two velocities are going to allow these objects to collide. So when I push play and I allow them to collide, something really weird has happened. All of a sudden, these objects are moving at very different velocities. And we're going to do that again. Guys, I want you to watch what happens to their momenta. The momentum of ball 1 was initially a half this way, and now it's 0.44 in that direction. It's changed its momentum. How is it possible that my teacher is telling me that momentum was conserved? Well, guys, the change in momentum of a single object, it's called its impulse. If I look at the whole system again, let's do some magic over here. So let's just reset this. Let's go back to our original values, and let's push play. Guys, if you take a look at the total of their momentum at the moment, if I add -0.44 and -0.06, what I'll find is still exactly the same total. Guys, you can set this up, you can play around with your masses, you can play around with your velocities.
Okay guys, I hope you're really enjoying this revision session. If you are struggling and need help, remember to post on the page or send an email to helpdesk@learnextra.co.za. Now it's time for a break, so don't go away. We'll be right back. Welcome back, guys. I hope you are getting into the idea of revision. Please let us know how you are doing. I'd love to chat to you guys either on the page or on Twitter. Enough of the chat. Let's get back to our revision now.
So the question is, why are we studying work and energy as separate things? If I do work on something, I give it energy. And this is where the work-energy theorem actually comes in. So if I do work on an object, one of the things that I say is that, well, here's a couple of points. I'm going to let you guys read them. I'm going to put them up on the screen for you. Let's just extend that. Let's just make sure that we understand what's going on. So why the work and energy theorem? Well, here we go. When a force is applied to an object while it moves, work is done. Sorry, I'm actually moving that off your screen. Let's just highlight that. There we go. So work is done when I'm moving an object. Guys, I want to make sure that people understand that if I push on something and it doesn't move, no work is done. There's no displacement, guys. If displacement is 0, work is 0. So let's take a further look. When there is a resultant or net force on the object, that object will accelerate. Guys, this is Newton 2 stuff. This is grade 11 work. So I know that this is going to be an acceleration. Guys, please highlight it. Make sure that you know that there's going to be a change in the object's motion, a change in the object's velocity. Now here's this is the part which really ties it together. The extra force. Guys, the technical term for the extra force is force net, or your F resultant. Whichever way your teacher explained it to you, that extra force which is left over after you've added up all your forces, that extra force or net force does the work that results in a change in the object's kinetic energy. There it is. A change in the kinetic energy. So this is the thing which does the work. Work and energy. This is the work-energy theorem, guys. I'm tying the two together. So the work done by the net force, so that's the extra force which I've got, is equal to the change in the object's kinetic energy. So let's see what the equation really looks like. So this work energy theorem. I've told you that the net work, so that's the total work done by the net force, or the work done by all the forces on the object, is equal to the change in the object's kinetic energy. Okay, so now, so what? I figure out that I've got work done by all these forces around the object, and that's equal to a change in the kinetic energy. How could this possibly be useful? Well, just remember that kinetic energy is a very useful way to find velocity. And that's very often where the questions go. So I'm going to try an example. I'm going to use the work energy theorem. I'm going to break it up into small pieces, make sure that everyone understands before we move on. Okay, so here it is. Here's my first example. This came from a past paper as well. It's not one of the ones which we've published, but what I've decided to do is to write it out for you. So let's use our work energy theorem. An object is pulled at an angle of 30 degrees, so there we go. We've already got an angle there to the surface with a force of 40 newtons. The frictional force experienced by the object is 12 newtons. Guys, there's now two forces. The object travels a distance of 3 meters under these conditions. Okay, so now let's just take a look at what the diagram looks like and where the object's going. I've just drawn in the displacement. There it is. Here's my displacement, 3 meters, my 40 newton force applied, 30 degrees up, and there, 12 newtons. Why have I drawn it in the other direction? Well, guys, friction always acts against motion. It always acts against my motion. Unless, and there are a few small cases where friction helps my motion go forward. Okay, but in terms of an object sliding over a surface by an applied force, friction is acting against me in this case. And it usually is, not always. Okay, so let's figure out what's going on here. Let's first deal with the applied force. Let's figure out how much work was done by that applied force. Okay, so here are my examples. I've got a force, I've got a displacement, I've got an angle between them. That's everything that I need. So there we go. I've got force applied, my displacement, and cos of the angle between them. So let's plug that into the calculator, and what do I find is that there is work done by the applied force equaling 103.92 joules. Now I just want to point out that it's quite significant that that comes out to be a positive value. That means if you do positive work on an object, that means that you give the object energy. I want that to be clear. If I do work on an object, I give it energy. That is positive work. What happens if I take energy away? Now, how can I take energy away from an object? Well, if you've been playing around with your energy skate park, I hope that you can see how that skate has started losing energy. I've got a stationary pendulum over here. Something took away the object's energy. And very often that is called a non-conservative force, but I don't want to get too tied up in terminology. But basically what I'm saying is that there's another force acting here which doesn't allow this object to keep on moving. There it is, my frictional force. So let's deal with the work done by the frictional force. And the equation is exactly the same. So do I have a frictional force? Well, yes, I do. I know that it's 12 newtons. Is there a displacement? Yes, I know that it's 3 meters. Now, cos of theta. Guys, this one's a little bit tricky. What I'm going to do is I'm going to put it in a different color. I'm going to take away all this other clutter. I'm going to make sure that people can see exactly what I'm doing. Guys, it's very important that you be able to get this angle correct. So let's just clean up my diagram. There we go. So nice and clean. Now that angle is probably the trickiest part to understand here. That angle is the angle between force friction and my displacement. Guys, friction is not acting in the same direction as displacement. They are directly opposed from each other. So here we go is my direction of my displacement. Friction is acting in the opposite direction. Let me see. I've got my displacement. It's half a circle away from my friction. So that is 180 degrees. So here we go. I'm going to use 180 degrees. And something really cool is going to happen. So I've got my 12 newtons. I've got my 3 meters of displacement. I've put them both in. So there we go. Tick and tick. We've taken care of them. Cos of 180. Guys, if you've got a calculator in front of you, I hope you do. Plug this in. Put in 12 times 3 times cos of 180. Close a bracket if you have to. and then press on the equals button. You say, hey Phil, something strange came out of my calculator. What happens is that I get a negative work. I want to see what that means. So what does it mean to do negative work on something? That means to take kinetic energy away from the object. And this is why objects under friction, or friction only, will eventually slow down. Because friction takes energy away from objects. I want that to be clear. Okay, so we're moving into the last phase of our question. Now we're going to use the work-energy theorem. So I figured out all the work done on the object. Let's add them all together, and then let's find the change in the object's kinetic energy. Okay, so there we go. Work net is equal to delta EK. So triangle just means change in kinetic energy. Anytime you see that triangle, guys, yes, it is Greek, okay, but it shouldn't be scary. Triangle just means change. So there we go. Work net is equal to my change in kinetic energy. My work on friction, there we go. We worked that out earlier. My work done by the applied force, all we need to do is to put in those values as positive or negative. The reason that friction was negative was because it took away energy. Work applied added energy to the object, and that was equal to the change in the object's kinetic energy. So that means that the object increased its kinetic energy by 67.92 joules.
Now it's time for a break, so don't go away and we'll be right back. Welcome back from the break. Please remember that this month is Library Month. We really think that reading is important and can be a whole lot of fun too. So remember to join in the chat on the page and tell us about the books you love. Look out for our book competitions too during Easter revision. We are going to have a whole lot of fun. But for now, let's get back to revision. Over to you.
Okay, well, what I've got here is an exam question, and this is from the November 2009. This is question 5. Okay, so let me actually write that down for anyone that's on the page. And guys, if you follow in my notes, there's a link up to the Department of Education past papers. So 2009, okay, just be careful. There are 2 2009 papers available on the website. This is one which was actually used. So this is November 2009, paper 1, guys. Paper 1 is the physics. Okay, so paper 1. Right, here we go. So we've got John applying a force F to help his friend in a wheelchair to move up a ramp of length 10 meters. So here we go. They've got a very nice drawing there for us, and a vertical height of 1.5 meters. Okay, so quite important that they've told me the vertical height there, as shown in the diagram below. The combined mass of his friend and the wheelchair is 120 kilograms, because mass very often is useful for calculating my kinetic and my potential energy. Now it says the frictional force between the wheels of the wheelchair and the surface of the ramp is 50 newtons. Now guys, just remember that friction always acts, and in most cases here, if I've got an applied force and there is friction, friction is usually acting in the opposite direction to the motion. It's stopping the wheelchair from going up the hill. Now it says the rotational effects of the wheels of the wheelchair may be ignored. So we're talking about any rotational energy and stuff like that. Guys, don't get too tied up in that. Don't worry about the rotational effects. Okay, so a little bit of fancy terminology, but don't worry about it. Now it tells me that the wheelchair moves up the ramp at a constant velocity. Guys, this is quite useful. Okay. I'm going to elaborate a little bit later on if we've got a little bit of time. I'm actually going to give you a velocity, and then I'm going to do P is equal to F times V. Because we've got a constant velocity, this is ideal. But the problem is there's usually a couple of steps before that involve the work and energy theorem. Okay, so they've asked us to do something very, very clever. They've said, what is the magnitude of the net force acting on the wheelchair as it moves up the ramp, and give a reason for your answer. Okay, so now let's just take a look and let's see what we've got, and pay attention to the mark allocation, guys. It's only for 2 marks. One of them will be for your answer, one of them will be for your reason. For 2 marks, it's very seldom expected that you do any sort of calculation or massive free body diagram. We can do one if you really want, but guys, it's not necessary for 2 marks. So let's spend our time on the things which do get us the marks. So here we go. we've got the magnitude of the net force acting. Oh, wait a minute. I know for this guy moving up this hill, I know that he's moving at a constant velocity. They've actually given me a very big hint. That constant velocity means that there is no acceleration. If there's no acceleration, there's no net force. Okay, guys, here we go. So there's your explanation and there's your answer. So we can say, if you want to explain it in terms of Newton 2, you can do this as well. You can say that F net is equal to the mass of the guy times by his acceleration. Well, we know that his mass with the wheelchair is 120 times by an acceleration of 0, because there's constant velocity. That's still equal to 0 newtons. So all the forces added up on this guy add up to 0 newtons. Now, guys, that is equilibrium. Now you might say, Phil, how is it possible that this guy is in equilibrium but he's still moving? Please, please, please don't make this error. Equilibrium just means that I maintain my current state of motion. That means that I stay stationary, I stay where I am, or I stay moving in the way that I was. Newton 1 is applying here. All the forces are balanced on our guy inside the wheelchair. So Paul is doing a good job keeping the constant velocity headed up the hill against friction and against the weight, but he's not adding to this object's kinetic energy. Now you might say, Phil, when did they actually manage to talk to you about kinetic energy? Well, if I read a little bit further, let's take a look at our question, and it says, what is the magnitude of the net work? Okay, wait a minute, this is something new. The net work done on the wheelchair on reaching the top of the ramp. Okay, so this is net work. All right, well, let's just write it down and let's see if we can get some ideas. So the net work. Okay, well, wait a minute. I know a formula for the net work. And if you were watching closely last week, the net work on an object is equal to the change in an object's kinetic energy. So EK, or guys, you'll see it on your formula sheet. Sometimes it says delta K. They don't mind which one you use because both are on your formula sheets. Okay, so let's work with this. The work done by the net force is equal to the change in EK. Here's the really magic part. Well, there was no change in the EK. So that is equal to 0. How do I know that there's no change in kinetic energy? Well, guys, let's pay attention. There it is. Once again, they're trying to plant the idea of a constant velocity. A constant velocity means no change in velocity. So no change in kinetic energy. Remember that kinetic energy is the energy of motion. If there is no change in motion, there's no change in the kinetic energy of this object. Now we're going to get into the interesting part of this question. So it says, what is the magnitude of the net work done on the wheelchair reaching the top of the ramp? And eventually we're going to get to the power of Paul if we get some time. Okay, so here we go. So we've got this wheelchair moving up the ramp at constant velocity. Here we go. Right, and then eventually I'm going to include something of my own. It says, calculate the following. First of all, the work done on the wheelchair by the force F. Now 5 marks. 5 marks tells me that there must be some sort of calculation going on. So work done on the wheelchair by force F. Well, let's look at our diagram, guys. Let's see what force F has actually got to do. Well, there's a few ways of thinking about this. Okay, so force F acts up the hill. Now, I find this diagram to be slightly confusing, and I prefer free body diagrams. The reason that I prefer free body diagrams is I can put these arrows wherever I want. So let's do exactly that. Let's just draw in another hill quickly. So let's have a green hill. So the wheelchair is going up a green hill in this case, and we know that this hill is 10 meters long. So what are the forces which are acting in the same direction as the motion of this object? Well, force F, we know, is acting parallel to the hill and up the hill. So let's just label it F as it goes. Now, there's a whole bunch of other forces, but what I'm going to do is I'm going to concentrate on the ones which are working against F. Here's the reason. I know that all the forces acting on this object, parallel and perpendicular, add up to 0. How do I know this? Well, they told me that the system is in equilibrium. The way that they told me this was that there is no net force. So let's take a look at my diagram and let's figure out what the other forces are. So what is force F actually trying to do? Well, let's see. So it says the work done on the wheelchair by this force F. Well, we know that we've got a distance of 10 meters. We know that force F is working against other forces to move it all the way up the hill. We know that all the work added up adds up to 0. So now it says the work done on the wheelchair by force F. Well, how do I do this with the information which I'm given? Well, before I start deconstructing all of this, I need to approach my work energy theorem, and let's do this with a little bit of caution. Okay, so already we established that W net is equal to the change in kinetic energy. Well, there's several types of work which is being invested into this object. There's work done by the applied force. So let's actually call that work F. Because it's force F, let's use work done by F plus. Now there's other types of work, remember. There's work which is done by gravity on the object. There is work which is being done by friction on this object. Now I've got to be very, very careful, but I do know that my kinetic energy change is 0. Okay, so very, very cool now. Now we are looking for this term. The work done by gravity. Now this one is quite a difficult one in the way that you do it. Okay, now I've got to realize that the work done on gravity is going to be negative work. Now I haven't talked to you in much detail about this, but work which decreases the energy of my object is called negative work. And the way that I find negative work is by investigating the angles correctly. So let's do work on gravity separately. Let's actually just make a little subtitle to work out my work done by gravity. So work done by gravity is equal to the force of gravity, and we know how to calculate that, times the displacement that was moved by the object and cos of the angle between. Now this is where it's about to get a little bit complicated. Between the actual displacement and the force of gravity. Now you might say, but we've been given an angle. Right? We can actually calculate this. We can play around with it. We've been told that the slope is 10 meters long. And we know that it's a certain height. Let's just check our information again. I think, there we go, it's 1.5 meters high. So it's 1.5 meters high. So we've got two displacements. Which one should I use? Well, when I'm using this formula, I have to use the displacement of actual movement. And herein lies the problem. Let's draw in my force. So there's my force. Where is my displacement? Well, let's draw in my displacement. Let's just make sure that everyone understands where my displacement is. So my displacement is 10 meters up the hill. What is the angle between them? Now, guys, this is going to require a little bit of calculation. So I'm actually looking at that angle. And this is a little bit of a pain. I'm going to have to do many, many different steps. There is an easier way. Now, my work done by gravitational force, and this is a little bit of a trick, and it is allowed to be used, is that work done by gravity is equal to the negative change in potential energy. Now, where did I get that from? Well, guys, this already introduces the negative part of this, the force gravity, and the delta x with the cos included. So what this does is this already calculates for us the work done by gravity on my object. Now, it should be a negative number. It's got to be a negative number, and the reason it's a negative number is because gravity is stealing energy from the wheelchair. Okay, so let's actually go for this. So I've got negative. Now, what was the mass of our wheelchair? 120 multiplied by 9,8 multiplied by the change in height, which is 1,5. So I've got negative 1764. So let's just make sure that we've got our substitution because you guys are making notes. So I've got 120, 9,8 over there, my change in height, which is 1,5. And let's just remind ourselves of that number. So 1764. So there we go. 1764 joules of energy is taken away by going up this hill. So there's two approaches to finding work done by gravity. This is by far the simplest one. If you'd like to, you can go and calculate that angle over there by using 10 as my hypotenuse, 1.5 as my opposite. Use sine and you can find out that angle and add 90 to it. But guys, unless your trigger is very good, I would suggest that work on gravity is negative change in potential energy. Okay, so now we've got my work done by gravity. So that's really good. There we go. We've got work done by gravity. What about work done by friction? So somebody said, what is the frictional force? How do I calculate it? Where does it come from? How does it act? Now, let's draw another little diagram. I'm big on diagrams. I'm sure you notice. I'm not the best artist in the world, but I love my diagrams. Friction acts against the wheelchair, pulls it back down the hill. So here's my frictional force. So my frictional force is acting backwards. Now guys, the displacement is up the hill. So there is my displacement. What is the angle between those guys? Well, this one's really easy. No big trig involved. Work done by friction is equal to, well, it's my frictional force multiplied by my displacement multiplied by cos of, guys, for a straight line, my angle is 180. This is a negative form of work, and I'm going to show you why. So let's just remind ourselves what the frictional force was. The frictional force over here is 50 newtons. It's inside my information. So let's use my 50 newtons. Let's use the displacement of 10. So there we go. We've got 50 multiplied by a displacement of 10 multiplied by, and cos 180 is negative 1. So what we've got here is negative 500 joules. Okay. So I know that friction is taking away a further 500 joules. Let's put it all together. 1764 and 500 both together. Let's put it back into my work energy theorem. So work done by F plus work done by gravity plus work done by my frictional force is equal to 0. Now, work done by F is what we want. Work done by gravity is negative 1764. Work done by friction is negative 500. And that all adds up to 0 because the object is not gaining any speed. So this is actually really easy to do. So what I'm going to do is I'm going to subtract a further 500, take it across to the other side, and what that would do is multiply it by negative 1, so 2264 is my answer there. So I've got my work done by my frictional force. 2264 joules of energy has been invested by Paul going up the hill. Now, what I'm going to do is I'm going to give a little bit of a challenge. We're running a little bit short on time, but I want to push you in the right direction. So what I'm going to tell you is that this wheelchair is capable of going up this hill at 0.5 meter per second. All right. So what I'm finding is that this wheelchair is going up there at a constant velocity of 0.5 meter per second. Guys, I want you to calculate the power. And to do that, I'm going to need to solve this next piece. And lucky for us, this one's really, really short. It says the magnitude of force F exerted on the wheelchair by John. Now, guys, this is probably the simplest of the calculations that we've bumped into this evening, because part 2 allows us to use our magic equation. So there we go. So work done by F is equal to F multiplied by my delta X and cos of the angle between them. But lucky for us, I'm looking for F. My displacement is 10. Cos theta is cos of 0 degrees. And my work is 2264. And what that allows us to do is divide through by 10. And my friction is equal to 226.4 newtons up the hill. Now guys, That's what you need to calculate the power. Guys, go for it. I want you to try and use the applied force. Remember the applied force pushing the wheelchair up the hill. You can work out, using the velocity, you can work out the power of Paul. Now, if you download those notes on the website, I've actually given you a really nice challenge on cyclists. Cyclists can maintain a really nice steady velocity. I've actually asked you to work out the frictional force of a cyclist, which can give out 300 watts and is able to maintain a certain speed on there. And you can actually calculate how much friction they're working against. You'd be surprised at how little it actually is.
Guys, we've come to the end of today's show. Thank you so much to Macmillan for making this wonderful show possible. And thank you to you guys for joining me and participating fully in today's revision lesson. Remember to visit our website, guys, for all your notes, all the videos that you need to watch from earlier on in the term. Our website is learnextra.co.za/live. Guys, if you're stuck or you need to ask any questions, please send an email to helpdesk@learnextra.co.za and let us know exactly where you're stuck so that we can help you even more. Don't forget to look out for more news on Library Month on our Facebook page as well as on our website. And guys, remember to join us for Easter Revision too. Bye guys.